Chapter 18 is called Vector Analysis, and some book calls it Vector Calculus. And I use the term calculus on curved domains. I think that's more explaining more about what this one is. So we've been learning calculus 1 and 2 and 3 so far, right? What are the domains? Calculus 1 and 2, what are the domains? Straight line, right? Calculus 3, integration, right? And all that, what is the domain? XY plane, right? So it's a flat, there's no curve. Or XYZ space, which is perfectly lined up, the coordinate system is all good. That's not curved. So doing calculus on the curved domain is what this one is, right? If you just compare or try to explain their title, vector calculus or vector analysis. All right? There are two things you're going to learn: continuing integrals, line integrals, and surface integral. That's all we have to learn in here. Integral on the curved domain. Main motivation of the line integrals is a physics problem, work calculation in the geometry, some important invariants in the geometry of complex numbers. That's how it started. Complex numbers are actually two-dimensional, right? Imaginary axis and real axis. Doing geometry in that, they discovered this invariant, line integral invariance. That probably motivate the definition of the work calculation in physics as well. And surface integral is called flux calculation. And I'm not going to attempt to explain this flux calculation right now. When we enter that, it's better. But this is the two things we need to conquer: line integrals and surface integrals. Okay? And then line integrals is I'm about to explain. Let me at least copy the title there. There are two types of line integral: line integrals of a scalar function and line integrals of a vector field. The book does not introduce line integrals of a scalar function because that's not the main focus, but other books usually do introduce line integrals of a scalar function. So I will just only introduce line integrals of a vector field. So you're going to learn line integrals of a vector field, but do not generalize that, oh, I know line integral. We only know at this point line integrals of a vector field. All right? So here's the main motivation. Going back to the physics problem, let's review. Vector R is a position vector. Okay, position vector, just one single vector. And sigma t is the vector function. Given t, it spits out R. Right? So R is the output vector, and sigma t is viewed as a function. But both are representing position vectors. It's a position vector, and this one, the value of this sigma t is a position vector. Make sense? Distinguish these two notation? Okay. And if you evaluate, differentiate the sigma t, then you get velocity vector, the value of this velocity vector, right? And remember this norm notation? That's the length of a vector, right? And sigma prime of t is the speed, not the velocity. Remember those? And if you differentiate it 2 times, this is the formal definition of acceleration vector. And your normal way of understanding what acceleration is slightly challenged here. But we just accept that. This is acceleration vector. More challenge is that if you look at this in a 3-dimensional way, acceleration vector, connecting your force as the mass times acceleration vector is even more challenging. This is really not challenging at all if it is just a linear. If you're pushing in a linear motion, intuitively it's really easy. But when you enter 3-dimensional space with this definition of acceleration vector, it's quite challenging if you think about it. But we accept that this is Newton's second law of motion. Okay? And F is just a force, just like this one R in there. One position vector F usually represent one force vector in particular position. Now this is a work calculation. If the gravity is acting on this situation, if there's some a ball is tied to the speed and the gravity pulls out, and you can see, imagine this moves downward like that because of the gravity. I'm focusing on the linear motion. So there's a constant force F is acting on to that direction. If I call G as a gravity force, we use orthogonal projection to get this purple component, right? Remember that part? And then that's how much force is actually acting on that ball. If it's perfectly horizontal, you can see it's not moving at all, right? But if it's slanted like that, orthogonal components kicking in and begin to move. If it is even steeper, and then because more force is kicking in, it moves faster and faster and stuff like that. So force multiplied by how much this moved is the definition of work in physics, right? And we have calculated this in Calc 2, right? Now we're entering curved domain. Not like this, curved domains. We're going from here to there, like that. Suppose there is a sigma t involved in there, and this is a sigma t k, and this is sigma t k plus 1 position vector. Make sense? And at that position, force is acting on like this. This is our force F. Good? And assume that tk and tk plus 1, the time interval is millionth second. So even though I exaggerated like curved space like that, even tiny time interval, this is almost straight line. So we decided to approximate this one with the straight vector in there, right? So, and even at this point, the force is different. Everywhere's force is different. It's not like constant gravity force. It is at each position and here and there, the force that's applied to that position is not constant, it's changing, just like that crazy vector field and trajectory that I showed you a while ago. But to make this one easy, they approximated this time interval is so small, so we believe, just assume that this force at that position is constant everywhere. And assume that it is not like this, curved. We assume that it's going to move straight forward. So it's instantaneous analysis what the physicists do, right? Assume everything is constant. We just move straight line here and constant force everywhere. Then we're going to calculate the length of this one, right? I'm going to call that one delta S. All right? And then this is approximated by sigma prime. Let me do it this way. This vector is approximately equal to sigma prime of tk. Would you believe that? This would be the velocity vector, right? But if t is small, t and tk is delta tk is small enough, this one is well approximated by delta sigma prime tk. This is huge size, but we're looking at tiny vector, correct? So you have to scale, multiply the scalar multiple to that one, so that it is a good approximation. Does anybody know what to multiply as a scalar multiple, so that this delta sigma prime tk would be the tangent vector, whose size is huge compared to this tiny segment? Not one of them. What's a good approximation? We use that to calculate the arc length. This was a delta tk. Delta tk is a time interval in there, right? If you multiply time interval there, think about how this one is defined. This one is defined by sigma tk plus 1 minus sigma tk divided by delta tk. That was a formal definition of sigma prime limit, right? So if you multiply delta tk back in there, it predicts this difference of this vector nicely. So that's the length of that vector. And they believe the length of this straight vector is good approximation of this curved line, the arc length, right? So what is the length of this vector in there? How do you do that? Norm, right? Norm the vector, delta tk times sigma prime tk. All right? That's the length of a vector. But delta tk is scalar and is a positive number, right? So we set it outside. and delta prime tk. So that's the approximation of this arc length right in there, right? But it is actually good approximation of this straight length. And then now we're going to calculate the work done to this path. So how much of the force is applied to that direction? Which is the old word, right? What is it? Orthogonal projection. So here is the ultimate challenge today. What is the orthogonal projection of F onto this vector? So that looks like good exercise number 2. Let's try that. Let's write that down. So the magnitude of the orthogonal projection of the vector F. The vector F is huge, right? Huge, and this line segment here, the vector segment is so small, onto the huge vector sigma prime tk. That's the exercise. The key is that I'm not asking you to compute the orthogonal projection vector, the magnitude of the orthogonal projection vector, right? Correct answer is the dot product of these two vectors divided by the first power of the vector or you're projecting onto. If it is not magnitude, you have square and vector is multiplied. This whole thing is a scalar, right? But the magnitude only picks up the first power. So that's how much force is exerted along this blue segment there, right? Fair enough? Okay. Then the delta W, K, the work done by this force over this tiny segment, which is in the correct direction of this delta K, but it is a lot shorter than delta prime, sigma prime K. So this is the work, which is this one, right? Multiplied by this is just scalar multiple. The length of this vector, correct? What is the length of this vector? We calculate it like this, approximate it like this, right? And it is this version right here. So let me write it like this. Delta prime tk times delta tk, right? Okay, so you see the cancellation. So what is what do we have at the end? This is the dot product of two vector, huge vector, right? Compared to the size of this one. It's a huge number multiplied by tiny number delta tk. That will be the tiny work done along the tiny segment of the blue part. Does that make sense? Okay, so that would be, millionth part of actual path. So what do we do to compute the total work? Riemann sum. The Riemann sum was the right word. So here, k going from 1 to n, how many division you had in there? There's what is this? Dot product of this force vector. Every position is force vector is different, right? Actually, multiply by your tangent vector sigma prime t delta tk, right? You sum up all that. That's a total work done along this path. So this is the Riemann sum where the delta tk is, and this is, everything in terms of tk. So this approach is from this integral where there's the scalar inside, but it is constructed out of vector functions, right? And this tk becomes dt. So the parameter t, however you parameterize this path, t equals a to t equals b. This is a total work of if you go from here to there, possibly in a three-dimensional space, and there's a force acting on like this, at this point, different amount of forces acting on that, and there's a different amount of force. These are the force at each of the point. And this is parameterized by whatever formula you have. And then if you calculate this one, then it computes the total work. Yes, sir. Oh, just a t. Sorry. Yeah. Should be t in there. All right. So we'll be focusing on this calculation. What's the good thing is one variable calculate, one variable integral, right? Not a double integral or anything like that. It's great, but it does some magic. So we'll explore that.